Hello, this is Team 3 and 4 from EE533, Network Process Design and Programming. Our project title is on in-network computing for real-time multi-sensor Earth analytics. The members of the Team 3 are Siddha Satish Kumar, Akshay Raj Kumar, and Shreji Kumar. The members of Team 4 are Hubayang, Yukun Lee, and Rohit Reddy. So our project is around in healthcare systems. Our ideas mostly based upon wholesale monitor, which are like portable ECG monitors worn by patients to continuously record their heart activity for 24 hours to 48 hours and alert signals to doctors if there's any abnormalities monitored. So this needs edge computing because we have to like be instantaneous and any detect any anomalies in the ECG detection. So considering this parameter, we thought of like going for our project on that sector because it's also not highly developed yet. So some of the symptoms we saw are trying to diagnose are AFib, PVC, VTAC, VFib, and depression and ST segment elevation. So we're trying to like diagnose these complex symptoms, and instead of doing it into a cloud-based system to diagnose them, we're just doing it on the edge, and which increases the latency and battery drain problems because again it's going to be there for longer time. So we want to have a better battery management. So this solution can be accustomed to based upon the health records and edge-based AI interference system to upload and classify the symptoms the doctor wants to diagnose. And yeah, reducing dependency on cloud will also enable us in running selected classifiers can also improve the battery life of the device and makes it potential for long-term monitoring and frequent hospital and without any frequent hospital visits.
Yeah, the thing that we wanted to add in the the existing Holter systems, like Holter monitor systems, is that our design might we can make it customizable according to the patient's need. So this will be based on a large model in the cloud and like a small model in the edge. Which can be customized according to the patient's record so that the uh, classification is done in a predict-with manner, and also it increases the accuracy. So coming to the system level design, we'll have a sensor layer where so each node in the net FPGA that will represent a sensor in the health monitoring system. So we could send data like heart rate, blood pressure levels, and other ECG signals from the nodes, and that data can be like processed into the the system. Yeah. So we have also have like a network and compute layer. So this is like the CPU GPU integration part. So instead of storing the data first and then later processing, we can just load it, like load the packets like directly into the like from the network, and then we can do the processing on the network. And then we also have a data processing section where it before we can have since we have like multiple nodes, we can like select the uh, uh, we can select the machine learning model that is capable of doing like the specific health function that we want to do. And then, we've also done the market research on this part. And this is one of the fast growing industries. And then, so since this is customizable, so we are expecting it to be expecting it to, and we are expecting it to work in the edge AI. So we can, and since the application is like very time sensitive, so we are expecting it to work reliably on compared to the comparing with the other systems that depend on the cloud. Yeah, now I'll be handovering the presentation to the to Hobo.
And thank you, Akshay and Shdas. Thank you for introduction about our system. And for this week, we also made a small system which functioning as a software part for our prediction for our ML learning part. So, what we did is actually we do the ECG with the heartbeat detection part on our like the whole stuff on our computer, which is software part. And what we do is we build a network. So the network structure, actually, I'm going to show you the structure. Okay. Okay, the structure is here. So what you have is going to have a convolution, 1D convolution thing. So the we separate it to two parts. The first is a feature extractor and also the classifier. So inside the feature extractor is what we want to do first on the software. And what we hope is in the future we can like put the whole network to our GPU, but we want to first separate it into two parts and we have a classifier. So this is what we're going to put on the GPU and CPU system. So for the feature extraction, we have one deconvolution. After that, we add a batch normalization, a ReLU, and also a max pool. And we have this kind of structure in 3 times. After that, we get a average pool, and also we flatten this feature. So the original one is 128. After that, we do the dimensional upgrade dimension, but we shorten the length. So the length shortened from 128 to 1, and dimension upgrade from 1 to the 64. So when it goes to the classifier, we have just one hidden layer to do this classify. So it goes from the 64 dimension features to two classifier. So this two class is one abnormal and two normal. It could be very different kind of tabs, but just for simpler representation, we just put it into two tabs at the very first time. So how do we get this system working is first we use the data set MITBIH. This is a data set which have a different kind of the patient's heartbeat record. It had a record normally from patient record 100 and patient record to 200. And normally the 100 record is more normal than 200. So in 100, we can say like, let me just get an example. In 100, we have this prediction like all zeros, which means it's all normal heartbeat. So I'm taking like the first 16 bit. So it's we can say, as you can see, it's all normal here. But when it goes to 200, like I just extract the first 32 bit, we can say like it's abnormal, normal, abnormal, abnormal. But so it's not a very uh it has a lot of abnormal in it. So we are going to use this. So what we're going to have is first feature extracted. We designed some script to do that feature extraction part, and I define in the model. So the model are separated from the ECG classifier extractor and ECG net. We are using this extractor, also the classifier in it to do the inference, which is the forwarding part here. So after extracted, we get the BF16 part features, which is here, this one. Yeah, we convert it to be a BF16 because normally in NumPy Python script we are using FP32, but we convert it to BF16 just to more fit on our GPU. And after that, we also need to get the width and also the bias for our system. So it's also in set. So it's also the BF16 module. So it's the same reason. We just wanted it to be more fit for our GPUs. And we are going to use this data for training, not training, but to inference our heartbeat, like the Akshaya and the should I say. So I'm going to handle this part, handle the system design part to the Shreyas, and he's going to show the how to mapping our normal CUDA code to the PDX and to our GPU's own ICC. Uh,
Hi, I'm Shreyas Dekumar and I'm part of Team 3. And pertaining to the project, from the technical point of view, like I have taken the responsibility pertaining to the compiler, API, kernel drivers, and basically the like implementing the bridge between the hardware and the software, and those related responsibilities. And from the business point of view, like I have taken the responsibility of being the storyteller by translating RTL into like simple language. So the first part, after having gone into the rabbit hole pertaining to this research, like the first part that we need to really decide is like what I've been going through is because of the fact that we team 3 have for CPU we have went ahead with the official ARM 70 DMI ISA and custom ISA for the GPU, and the parallel team 4 has have their own ISA for their CPU and GPU, and so what I was doing is like just to see what is the best way possible in order to merge both the ISAs, like in that would not be like too strenuous on us in for by change like in order to not change too much of the code as well, but at the same time it's like an ensemble of both the teams. So I have been working on that, and the next key deliverable pertaining to next week's Monday's video is that we finally come up with the final ISA that which will be an ensemble of both the team. So that is one of the deliverables pertaining to the next next week. Narrow down on the ISA, and the second part is like I've been working on have started working on the mapping layer slash the just-in-time compilation that is as a test slash a debug software between the hardware like between the CPU and the GPU that maps as I said, that maps the CPU and the GPU core. And for that, I just came up with a basic. It's still work in progress, but the host code which will run on the ARM CPU core if it's pertaining to our design, and the kernel code which would run on the GPU. As you can see, the bfloat instructions are present. And the mode of execution, because of the fact that I don't possess an NVIDIA GPU, I'm going to use Kark on demand, and for that I'm just going to submit the make changes accordingly to the job file and the make file accordingly, and use Karks on demand to test the process. So yeah, so this is what I have been. This is what I started with, and yeah, now I'm gonna hand over the next part of the project to my teammate. Thank you.
Hey, hi everyone, I'm Rohit. So now I'll talk about the hardware changes that we need for for our project. So as teammate said, in this project, so each node will act as a each sensor will act as a node in the network, and each node will write the data to the FIFO that's present in the data path. So in order to modify the or compute on the data that's generated by any of the node, so we have a CPU GPU system that's integrated with the user data path, and we have a common data memory between CPU GPU, which is same as the FIFO. So we have so then we would need like additional instructions to access the FIFO and communicate with the data path. So if you look at here, the FIFO instructions. So these are the instructions to uh, to control the FIFO. So basically, when a node writes data to the FIFO, when a packet is received, so it will be stored in the FIFO, and so these are the signals that the CPU will receive from the FIFO system. So so where the offset is like so the packet offset, like starting address and ending address of the offset of the packet, so that we could process the data that is between in the that is between the starting and the ending address. So and we further have like two instructions. So this will send a signal to the send a signal back to the FIFO saying like now the data is ready. We have done necessary computation on the data, and now the data is ready to send to the target node. So we have this signal, we have the new instruction added to our ISA, so that whenever this instruction is executed, uh, the packet will be sent to the target. And similarly, we have FIFO wait, so that this instruction will stall the CPU and wait for the uh, a packet to be received in the FIFO. So these are the instructions that we added newly to the CPUs uh, uh, to uh, like modify the payload of the to modify the payload. And this is a instruction which we added so that there will be a handshaking between CPU and GPU. So for that we have used it. We have added like two new instructions. So one is to run this GPU. So when we execute this instruction, so GPU will have the entire control of the data memory, and it can do uh, load stores on the data memory, manipulate and update the data memory. And this is and we have one more instruction WRP. This is to write the param registers of the CPU, so that we can do like required operation, like we can select between the operations that we want to do on the GPU. And now to test all these things, we have a like a simple program to test whether we were able to manipulate a packet that's there in the data path. So the simple code, what it does is it waits for the uh, before to receive a packet, and once it receives a packet, uh, it's loading the data that's present in the address 6, and it's adding 2 to uh, the data that's already there, and it's again storing back to the same address. And at the end we are running before done, so this will give a signal to the data path, so that so it so when at the end like that means we are saying we have modified the uh, we have done the required modifications, and now the data is ready to transmit to the target node. And yeah, so this instruction does send that signal to the FIFO. And yeah, so this is our whole code, and now you can will give a demo of this uh, whole code and working on the FIFO.
Okay, so I will explain how the whole system is working on the hardware. So basically, you could imagine like our node 3 is some of the patients, like there is we are collecting some data on it, like it's very simple data. It's just 1111 and ahead with some zeros. But later we will apply this to the real, like some heartbeat data. So now it generates this kind of data, and it will send the packet like to some terminal or to some receive node. And for currently we are using the node 2. We are using the node 2 for receive. And then wait a minute. And then this is our build hardware systems. So for currently we are using the instruction set that Rohit provide to us. This one. Let me check. Mm, yeah, we are using the iMemory modify packet that it adds to one of the data, and then it send it out. After we doing finish the modification of the GPU, we could apply some Mac to it. Then it's our final propose it's our final projects as a target. And for now, it generates some data, and then it send the package to the terminal, and then we send it, and then we could find that we do add some two to this one, and then we could check of our hardware's memories. Like let me check. Yeah, like we could read, and then yeah, it do add to some displays. And wait a minute. It is because, sorry, we don't listen at this port. It means nobody is receiving data from this port. So the packet sounds a little bit weird because it sent out some packets. This time it should be work. Yeah, you could check that. This is our data, and then we add two to some of the zeros, and this is some headers of the packets. So this is our whole systems on hardware. Thank you.